So we have some homework we're taking out, and let me review something called a Danielle cell again. Okay, we have it up here, and it's an application, or it's an example of a voltaic cell or a galvanic cell. And we should be able to do the following. Now, there's a whole bunch of resources that are there for your viewing displeasure. However, this is nothing more than an application of all the oxidation reduction principles we have learned. Okay? So, first and foremost, we had zinc and copper. And the first thing that we do with an electrochemical cell, especially a voltaic cell, is what? What do I do? What's the absolute first thing I do when I see a voltaic cell? Not good. Not good. Okay, someone said it. Yeah, you got to see who's best at oxidizing. Now, I have net potentials listed up here, but it's the same list on table J. So I've got my copper, who when it oxidizes, its potential will be negative 0.34. We all know that the copper is the metal that did not react, okay, in the acid or the water in our last reactivity series. Then if we look for zinc, zinc is much higher. So comparing zinc with copper, and this is the same list on table J. If you cut all of this out, cut all of the voltages out, and you have this list, it's the same list. Zinc is higher than copper. So zinc is better at oxidizing, which we remember something. We have, this must be the what? Remember, anox. So the one who oxidizes, which is my tin, is the what? The anode or the cathode? Anox. Yeah, the one that oxidizes. The one that's better at oxidizing is the one who has to oxidize. So that is my anode. Therefore, my cathode is the copper. Now, the mnemonic we remember is anox red cat. Very helpful to us because it helps us remember that the cathode is where we're going to have reduction, and anox, the anode, is the place we have oxidation. Now, we're going to assign some charges here. Now, these charges, do they exist in nature? No one discovered them. It's a convention. A convention means it helps us figure out, Jackie, where electrons are coming and going from. We're going to give the anode a negative charge. We're going to give the cathode a positive charge. Now, the reason we do that, and if you look at your car batteries, okay, if anytime you're helping your dad or mom jumpstart your car, if you ever had to do that, you'll see that your car battery has a little negative sign and a positive sign in the battery. The negative sign will go to the anode, and the positive is the cathode. Very important. Now, we have to understand that the zinc is better at oxidizing than the copper. So what is the zinc going to do? Well, the zinc, 0, and this is important, the 0 means it's a solid phase. Any metal who has a 0 charge is in the solid phase, except for mercury, but we're not going to deal with that. Zinc loses 2 electrons and becomes zinc plus 2 in the process. What does that mean? That means a piece of zinc becomes zinc plus 2 in solution. When you are charged, you're now aqueous. So what's happening to the mass of my solid zinc anode? The mass is getting what? Smaller. Very important. Now, as zinc gives up 2 electrons, these electrons go from the zinc through the wire and then back to the cathode. And you should know electrons always flow from the anode to the cathode. Why does that make sense? You can memorize it, but why does it make sense we go from the anode to the cathode? Negative to positive? No. Because we made the negative positive. Who's giving off electrons? The one who oxidizes. This is the oxidation cell. This beaker, we're losing electrons. Don't lose sight of what this means. What? Leo. The lion says grr. This beaker is losing electrons. this beaker's going to gain them. So if I separate my half reactions and separate them out of touching, they have to flow through the wire. So the reason why electrons go from the anode to the cathode is because it has to go from the one who produces electrons to the side who accepts them. Now, who's accepting them? Because this gets a little confusing. We said that the anode is the place of oxidation. In this battery, it is actually undergoing oxidation. That's my solid right here. The cathode, you might think, is the one that undergoes reduction. But really what it is the place for reduction. Electrons travel through it like a conductor from the anode through the wire back to the cathode. Now, these electrons are here, and they're on the metal. In the solution, you see it's blue, don't you? The copper plus 2 in solution pulls, or it's attracted to, and it absorbs them. And what happens is copper plus 2 gains the 2 electrons that came from the zinc and made pure what? Copper 0, which, my friends, in chemistry is solid. We're taking the solid piece away to make the electrons and the zinc plus 2. And when this comes here, this plates. Plating means you went from aqueous to solid. So the cathode, its electron is gaining mass. It's getting bigger, yes?
Transferring electrons.
Yes, it is. And that's what a DC current is. It's a transfer of charge. Now, I want you to think of this. I told you a voltage represents a potential difference. It's a force. Think again of my analogy in terms of a waterfall. Higher the waterfall, the greater the distance between the top of the river to the bottom of the waterfall, the greater the force of the water because of gravity. Well, that works the same way. What creates the voltage, the force that pushes electrons around or charge around, is that this guy is pushing its electrons through the anode to the wire, and it is the copper plus 2 that is specifically pulling the charge. Zinc spontaneously loves to oxidize. Zinc, when it oxidizes, is plus 0.76. Copper, when it reduces, copper plus 2 in solution, when it gains 2 electrons, is positive 0.34. So they're both pushing and pulling. And when you combine their half reactions, and let's do that right here. We have zinc 0 going to zinc plus 2 and 2 electrons. And is this a good balanced half reaction here? Is the charge in both sides the same?
Yes.
Good. Then we have copper plus 2 gaining 2 electrons to make copper 0. Is that a properly balanced half reaction? Correct, because both sides have the same charge. Now, let's do the net potentials. Zinc oxidizing, going this way, you change the charge, is positive 0.76. Copper reducing, plus 2 is, oh, not that one, plus 2 is positive 0.34. Notice they're both positive. When you add them together, of course I know this is the cathode, it's in my way now. What do you get? You get 1.1 volts. Positive 1.1 volts, which tells me what? This works. This is going to happen. This battery is going to run spontaneous. Spontaneous means it works. Electrons pass around. He's good at pushing electrons, so his part of the battery is 0.76. Copper plus 2 is good at pulling them or accepting them. His part is 0.34. You add them together. If I'm going to push and Reese is going to pull, we're going to have a collective force that's bigger than both of us. That makes sense? If I'm going to push something and someone's going to pull, it's the combined efforts we get the total voltage. All right? And that tells us battery works. But why isn't my battery working right now? What am I missing? You're missing a salt bridge. Okay, so without a salt bridge, no matter what elements I put in my battery, it's not going to work. So once I put in the salt bridge, now I'm going to have some voltage. Maybe, if these are just a little bit closer. So now I have a voltage. And you say, Mr. Grodsky, why isn't it 1.1? Okay, and the reason is that my concentrations are changing. It's really a discussion for AP Chem, but it's less than 1. But the maximum that I can have is 1.1. So over time, this is going to die. Can you guess what's going to happen when this is going to die? Now, before we get to that, why does this salt bridge, this U2, what is it doing? I'm going to get rid of this point right here. Okay, we get the idea that we have positive volts. What is this U2 salt bridge doing? Why is it allowing the voltage to go? What's it doing? It's important. This is important parts. Yes? Maintain electrical neutrality. That sound familiar? Yeah. Now, without the salt bridge, we had 0 volts, correct? No salt bridge. What do we get for voltage? Nada. Sorry, not even there. No salt bridge, nothing. Salt bridge, right over here. No salt bridge, you get nothing. With the salt bridge, you get a voltage. What's it doing? Notice it's now 0.95. My battery's dying. What does it do? Maintain electrical neutrality. What? Well, in my salt bridge, I have 2 things. I have Na plus and Cl negative ions. Now, over time, what's happening to the amount of my solid zinc? It's becoming what? Zinc plus. It's becoming zinc plus 2, right? What's happening to the amount of my zinc plus 2 over time? It's increasing or decreasing or staying the same? It's increasing. This beaker is getting positive. Why would electrons be pushed away from a positive? This beaker is positive. So what happens is, in the salt bridge, negative ions are allowed to come down and enter to do what? To alleviate the buildup of positives. So as this becomes positive, the negatives are drawn through the salt bridge. Negative ions. There is no electrons, Jackie. No electrons travel through the salt bridge. It's just ions. So the negative ions combat the positives that are being released. Over here, I'm losing copper plus 2. Over time, the amount of positives are decreasing. So to replace the positives, the sodium comes down to keep this beaker from losing its positives and becoming negative. And we get the negative ion coming down to keep this beaker from getting positive as we increase. So the negative ions rush down here to neutralize these positives, and the positive ions come down here to replace the positives that are lost. That's how we keep each beaker neutral. I know that we're putting signs here, but that's for us small-minded people to understand. The negative sign tells us, hey, electrons are popping out of this one. This positive tells me, hey, electrons are going toward it. That's your battery in a nutshell in a classroom. Every single battery, Voltaic cell or galvanic cell, has these principles in them. Every battery has this principle. Okay, so it's very important you understand that. Okay, so for homework last night, I asked you to do this again for somebody else. So on the other side of that worksheet, let's pull that up. Okay, so I asked for work of home to do this one. Lead and copper. And I asked for the reduction net potential, and I asked you to do all of this. Okay, that was your homework. Yes? Okay. All right, first step, I look at this battery. Who's my anode? Who's my anode? How do I know it's lead? What's the first thing that I do, party people? I had lead and copper. The first thing I do is see which one is better at oxidizing. Absolutely. So here's my lead, and here's my copper. Who's better at oxidizing? Lead. So who's the anode? Anox. Lead. That's the first starting point. If you can't do that, the rest of this doesn't make any sense. So real quickly, we get lead is your anode. Now that tells me that's the place of what? Oxidation because of what? An ox. Whose copper must be the what then? The cathode, because I know if this is the anode, because of this one being better at oxidizing, this must be the cathode. And I remember the mnemonic, red cat. Reduction occurs at the cathode. Okay, here we go. Now what happens? Well, at the anode, anox, there's oxidation. So the oxidation half cell, let's go here. That's the part of the battery. Okay, we have Pb what? 0, correct. The solid metal gives up 2 electrons to become Pb plus 2. Kind of gave that away right here. So what does that mean? A piece of lead right here, solid, becomes Pb plus 2. The piece of anode is decreasing in size. And when that happens, 2 electrons are popped out. Now, where do they go? Well, lead is pushing the electrons. Electrons always flow from what? From the anode to the cathode. We'll pretend this switch is closed, okay? And we go through the voltmeter that measures that push and pull. And our electrons are going to build up right here on the cathode. Now, what's going to happen at the cathode? Well, red cat. There's reduction. Now, here's the mistake people make. Can copper solid, copper 0, ever get reduced? No. Standalone metals can only what? Oxidize. So this is not going to reduce. It's just going to be the place where reduction occurs. It's actually going to be the copper plus 2 ion that's involved, just like our Danielle cell. So the copper plus 2 is going to grab or be a trick these 2 electrons. And what happens is, right, here's our reduction cell, copper plus 2. In this case, absorbs the 2 electrons that the lead lost and becomes Cu0, which means it made solid copper. And you should get this. The copper gets bigger. The ions come out of solution, it becomes less bluer, and this gets bigger. The mass of the cathode gets bigger. For the next cell that we do tomorrow, plating always occurs. You electroplate. You're putting ions into a solid. Plating always occurs at the cathode because plating is reduction. Now what's the voltage? What would be the voltage of the cell? Well, if I do my net potentials, I got to find it. So my voltage would be lead plus 2, or lead oxidizing is what? Positive 0.13, because I'm going that way. So it'd be positive 0.13. I'm just going to put that there. And what would be the one for copper? Well, I know it because we kept using it. It's the same one we use here, but for those that don't, copper plus 2 is what gets what? Reduced in solution. And copper plus 2 getting reduced in solution is positive 0.34. I don't flip this sign because this is reduction. So positive 0.34. And I put that there. All right, positive 0.34. Add it together. What you get is 0.47. I don't know where that line came from. Positive 0.47. What does that mean? It's spontaneous and it works. Now, do you need the net potentials to tell you that? Table J shows lead above copper. So this will work. Okay, what else am I missing? What did I ask for? Flow of electrons, flow of ions. Ah, sodium nitrate is in the salt bridge. What does sodium nitrate break apart into? Let's do that. Some people don't see that. Sodium nitrate is NaNO3. When it breaks apart into ions, it breaks apart into Na plus and NO3 minus. So my friends in chemistry, in solution, we have this aqueous ion and this aqueous ion. So I've got Na plus. I don't think that comes out very well. Let's pick a different color because I can. So Na plus, okay, and then NO3 minus. Now, where do they flow? Over time, in the oxidation side, the place that's the anode, anox. Leo, the line says, Gert, losing electrons. It's all the same stuff. I'm losing electrons because I'm building up Pb plus 2. The result of passing electrons is that this builds up. So we got to combat this increase of positive because electrons can't go away from a positive by what coming down? How can I make this electrically neutral? As positives are building up, as this goes forward, NO3 minus has to come down. The negative charge comes down. So the negative charge comes down. Through the salt bridge, ions flow. And they keep this beaker from getting positive. What about my reduction half cell? Copper plus 2 is gaining electrons here. We're losing the plus 2, so this is getting negative. So the positive ion rushes down. All of this you're held accountable for. And that makes our battery work. Okay? Now, notice the voltage here is 0.47. What was the voltage here? 1.1. Why is the battery with lead lower in voltage than the battery with tin? All I'm doing is same copper, but now I have lead. Why was the voltage higher with tin and lower with lead? Copper's the same thing. I'm just going to switch out the lead. Why is it lower? Yes. It's worse at oxidizing. What creates the voltage, guys? The push and the pull. Where did my voltage do? I went down. Why did it go down? Because lead is not good at pushing as well as zinc was. Copper plus 2 are still doing what? Doing the pulling, which adds to it. But lead isn't good at pushing as well as zinc does. So therefore the voltage is less. Can anyone guess who would give me the greatest voltage? Which metal? This is really important. Which metal? Let's go back to our chart. Which metal would give me the greatest voltage? Lithium. Ever hear of lithium-ion batteries? That's why they use them. And they're actually very light. Yes, Reese?
I was 0.55 over 0.47.
I'm sorry?
If you go back to
What I have is, if I throw it in its own concentration, I've got other ions in here. So let's try it, another concentration. If you change the concentrations, you can mess around with the voltage. Right now I just threw it in there, but let's just put it in a lead nitrate solution. I've still got some zinc ions in there. So let's see what happens now. Okay, so that was my zinc. Here's my salt bridge. And I'm guessing this is lead. This may not be. This is lead. Still a little lower. Now, we'll learn this next year. When you change, the concentrations are the same. Believe it or not, Le Chatelier's principle. Right now I have lead. If there are more lead plus 2 ions than copper plus 2, the reaction is forced forward to create more voltage. This is a voltage under standard conditions when the concentrations of everything are 1 molar. But if I can make more voltage happen if I increase the concentration. Now what happens over time in my battery, you're going to run out of copper plus 2, aren't you? Le Chatelier's principle states if you run out of one of your reactants, the reverse reaction happens. So the reaction that I have here is not zinc anymore, it's what? It's lead. So here's the overall reaction. This is lead plus 2, but the overall reaction is Pb 0 plus copper plus 2 goes to Cu0 plus Pb plus 2. Now he's asking me why it's greater than up here. It might be because I have a lot more copper plus 2 if this is higher than this value here. So if there's a huge amount of copper plus 2 compared to the Pb plus 2, the Shatler's principle states if you increase the amount of 1, it's going to shift to lower. Therefore, I'm going to cruise more. If I'm going to go forward more spontaneously, the voltage goes up. Great question. Yes. And that explains why the battery dies. Once I start running out of copper plus 2, the reverse reaction wants to happen. And that's what you do not want in a battery. You do not want equilibrium. If the battery goes to equilibrium and you have a reverse reaction, think about it. I got water flowing downhill. I want a great amount of water. If water starts flowing uphill, okay, it kills the force. Voltage is a force that pushes the charge around. Yes, Kara?
So can you force a reverse reaction if the reactants haven't run out? Like when you charge a device and it's not totally
Yeah, exactly. So what happens is in this battery, this is a lot like we talked about yesterday with your phone, you plug it in. So what's going to happen, now it's not the same system, but the same principles. So spontaneously this goes forward, which means this goes down, and you could run out of lead, a lead solid. And what could happen is you could run out of, this goes down as well. You could run out of both. Now, spontaneously, it likes in light, the nature of it, it goes forward. It's positive volts. What does that mean? Gibbs free energy? We can use energy because the rock is rolling down the hill. And to get the rock back up the hill, we have to do what? Add energy. So positive volts makes naturally you go this way. That means positive volts. To make a reaction that does not want to happen, I add voltage. Copper does not want to oxidize, does it? In your lab, did it oxidize? No, so for copper to oxidize, it's negative 0.36, correct? So that would force copper, if I plug it in, to reform copper plus 2, the reverse. So by charging your battery, you're making the reverse reactions that don't normally ever happen, and you're replenishing the what? The copper plus 2, and you're making Pb plus 2 become Pb0. Look at this, Pb plus 2, look, Pb plus 2, down here, does not want to become lead. Pb plus 2 does not want to gain electrons and make lead. Look at that value. You plug it in, you force it to happen. So you're forcing the reverse to happen by adding energy, and that's so important for tomorrow. This system, when it works, gives off energy. This is an exothermic reaction. But then when it runs out, you plug it in and force the reactions that don't normally occur natural to happen. Anytime you got negative volts, that doesn't happen. That means that's what you have to add to make it happen. Okay, it's important because the next cell that I teach you tomorrow is going to have scenarios where you need energy to force it to happen. Gold plating, those kind of things. Okay, let's go to the other questions here. Let's go to the other side of that worksheet. All right, not this one. Let's go here, other side. Okay, here we go. This is what you are responsible for to answer. Here we go. So given this picture of the electrochemical cell, in this case it's a voltaic cell because I see a salt bridge, they're going to ask some questions. Before I can ask the questions, you have to get your parameters set. I see 2 electrodes. Before I can ask any questions, I have to figure out who my anode is to see where the electrons are flowing, which side is oxidation, which side is reduction. So my friends in chemistry, looking at magnesium and copper, who's the anode? Now if you don't know, where can you look? Table J, but you don't have to because I gave you the experience in lab. Which metal is more reactive? Which one reacted in water to give you that pink color because it made a base? Which one gave a lot of fizzing in acid, and which one looked like it did nothing? Who is more reactive? Magnesium. If you don't believe me, go to table J. Magnesium clearly is more reactive. You never make a car out of magnesium. It's too reactive. Copper, yes, but they'd be too expensive. Now, so magnesium is higher on table J. So, mark it up, guys. The first step is see who your anode is. So I'm going to mark it up and say, magnesium is my anode. Now some people like to say anode, but anode. Copper is my what then? Cathode. Now, once I know it's my anode, anox, this is the side that oxidation occurs. We know oxidation is Leo. The cathode, because of a red cat, this is a side reduction occurs. Reduction is what? The gaining electrons. So what's going to happen? Electrons are going to flow away. Well, let's look at the questions now. Number one, the oxidation half reaction that occurs in this cell is what? Well, if this is my anode, then oxidation occurs here. So it will be 4. Mg0, which is solid, becomes, and draw the arrows so you see it, party people. The solid Mg gets smaller. A piece of it goes missing as it makes Mg plus 2, and then it produces what? Electrons that flow.
Mr. Gronsky, this is confusing. The last two ones you did went left to right. I thought the anode was always on the left.
Don't be a robot, okay? It can go the other way, okay? Don't fall in love with the fact that I had 2 examples where the anode was on this side. All right, so it's going from the anode to the cathode. So, yeah, number 1 is 4. Now, before you check off these, when you are given a redox reaction and you're given a choice regarding oxidation or reduction, make sure your half reaction is correct. This is 0 on this side, plus 2 and a negative 2 is 0. Just make sure you always check that your half reaction has the same charge on both sides. 4 is the answer. That's not tough, is it? No. Okay, when the switch is closed, the E0 of the cell is what? Well, we have Mg0 becomes Mg plus 2, and it gives off 2 electrons. And then we have, what's happening on the other side? Electrons occur. Copper plus 2. In solution, gains the 2 electrons and becomes copper 0. Now we should know that the copper reducing is positive 0.36. We've been using that for 3 examples now. Positive 0.36 volts. What's magnesium? Well, you should know that off the top of your head. If you did, you need to find some hobbies in your life. Well, I was studying all of them because I thought that would be fun. Okay, well, all right, I guess it's fun. So, magnesium plus reducing is negative, but I want the oxidation so that becomes positive 2.37. So positive 2.37. Positive 2.37. Add them together. 7 and 6 is 13. You get 367. 2.73 volts. Notice it's positive. Notice that this battery, yes, ma'am. Is it 3, 4?
Yeah.
Okay, so I didn't remember very well. Oh no, he didn't. Okay, yeah. So positive 0.34. So that gives me 11. Okay, 2.71. Thank you very much. Okay. Notice this gives off a lot more volts than what? All the other batteries. Why? Magnesium is more, it pushes more. Okay, this is magnesium. Okay? This is lead.
What about lithium?
This is copper. AU is, again, there's no energy. Okay, what about lithium? Okay? All right. Sorry. All right, now, next question. So number 2 is definitely positive if this works. Number 4. Okay? Yeah, baby. 3, the substance that gains electrons. Who gains electrons? Careful. Who specifically gains electrons? I see you too, that's cute, but Cu plus 2 is the one who specifically gains electrons. If you said Cu, I'm going nuts. You always choose what? Right, you may not see that, but that's the concept. You don't pick copper. Copper does not get reduced here. Copper plus 2, so good job for those that saw that. I see you out there. Okay, so copper plus 2. Number 4, when the salt bridge is removed. When the salt bridge is removed, what happens to the voltage of the cell? It goes to 0. So number 4 is the answer. Who is the anode? Mg what? 0. Now listen to me, party people. The anode and the cathode have to always be conductors. Even though in our half reactions, we say that copper plus 2 is specifically getting reduced, the electrodes are the conductors. So therefore, the cathode is still going to be pure copper. We're not saying the copper is getting reduced. We're just saying the place of reduction. So the species that is the cathode is the copper. Okay, where do electrons flow? From the one that gives off electrons, right? So electrode that is oxidized. The electrode where reduction is occurring. So 2 is the best choice. Not written very well. I feel bad. But from the anode to the cathode. Anode is oxidation, to the cathode, red cat. Salt bridge provides a pathway for what? Ions only. If electrons travel, and people will pick this, if electrons travel through the salt bridge, why would they ever go through the wire? They pick a path of least resistance. So ions flow to maintain electrical neutrality. Which one is gaining mass? The Cu is gaining mass, or you can say the cathode. Cathode is gaining mass because of reduction. Who's losing mass? Mg, or the anode, always. Okay? And if you're not sure, party people, go to your half reactions. Okay, so tomorrow we are going to do a lab. You're going to build a battery. If you do it successfully, you're going to run a radio. Now, work of home. I'm going to post 10 questions on voltaic cells. I'll have it posted. It will be a form. See you tomorrow.